All right, so today we're going to talk about calorimetry, and this is in order to get us ready for our lab on Monday. So, you do need to make sure that you do have an understanding of how to use what we call the Q equals MCAT equation, because it's going to help you with that lab on, like I said, the lab on Monday next week. I don't know if I say Tuesday or Monday. Anyways, the lab's going to be on Monday next week. We're going to try to do two things. We're going to try to have you identify a piece of metal based on its specific heat, and then also have you figure out how many calories are in a single cheese puff. So that's what we're looking to do. So we get to play with some fire on Monday, but it's only going to go well if you understand the calculations. So here we go. So there is a paper, so please make sure that you are looking at it. Most of it is already filled in. The only thing that you're filling in is the example questions. So units we use for heat and energy, you've already been seeing them as we've done assignments and as you've looked at problems. Joules is the most common form of energy measurement. It's kind of like a generic. Okay, so joules. You'll also see kilojoules. Like you've seen that a lot, kilojoules. All that is, that's just a metric prefix. It means 1,000 joules. So like if you see 1 kilojoule, instead of saying 1,000 J, it just says 1 kJ because that's the same thing because kilo means 1,000. What you commonly see if you take a look on any of your food or your drinks is you see calories. So you actually see big C calories. So little c calories is used for food energy content, but how we report it is using big C calories. And big C calories is equal to 1,000 of the low calories. Now, what exactly is a calorie? It's how much energy it takes to increase 1 gram of water by 1 degree Celsius. So that, in case you've ever been wondering, like, what exactly is a calorie? What does it mean, a calorie? That's what it's talking about. Okay, so how much energy does it take to increase a gram of water by 1 degree Celsius? And it is a study of heat transfer in chemical and physical processes. And it works by determining the amount of energy flowing from one system to another. And we have a good equation. So the equation is Q equals M times C times delta T. And because a delta kind of looks like an A, we usually just call this the Q equals MCAT equation. So if you hear us say Q equals MCAT, your chemistry teachers are being funny and you hear Q equals MCAT, what the heck is that? That's what we're talking about. So Q stands for energy, and it's either energy that is absorbed or released. And this still comes back from endothermic and exothermic. Remember that if you take in energy, you have a positive number. If you release energy, you have a negative number. And then M stands for mass, and that's always going to be in grams. C stands for something called specific heat capacity. And what that means, what that is determining is like how fast can it heat up and also how fast does it cool down. So, like water has a very high specific heat capacity. It takes a lot of energy to get water to boiling, and then it takes a really long time for that water to cool down. So, think about it. We're getting close to summertime. If any of y'all happen to have an outdoor pool, like whether it's a kiddie pool or whether it's, a nice above ground, in ground, whatever, if you, like you don't fill it, you don't leave it filled all year. So you're, like maybe you're filling it now, the water's cold right now, but as it warms up and everything, as the sun shines, it's going to start to heat up. But it takes a long time for that to happen. So that's the specific heat capacity. Like how fast does something heat up and how fast does it cool down? And then delta T, there's our famous little delta symbol, which means change in temperature. And delta T is always equal to final minus initial. Or delta is always final minus initial. Delta T, since it's T, which is temperature, it's going to be your final temperature minus your initial temperature. So you do have a triangle to use again to help you with the math problems. Remember once again how to use a triangle. Whatever it is you're looking for, you cover that up. Whatever is left, that's what you're doing. Remember, if the values are side by side, then it is multiplication. If it is top and bottom, then it's division. So the big thing is, because this is like doing just a specific calorimetry problem is not difficult. Like doing a Q equals MCAT problem, this doesn't really pertain to that. But for what we are doing on Monday, it is important that you remember that in a chemical reaction, this is what I tried getting y'all to write on the back of your heat transfer notes from the other presentation. about the law of conservation of energy. So heat, which is energy, has to be conserved. So if heat is being lost by something, it has to be gained by something else. Okay, that is the law of conservation energy. Energy cannot be created or destroyed. It's just like mass. Can't be created or destroyed. It can only change forms. So energy can go from chemical energy to heat energy to potential energy to, whatever. But it just can't be destroyed. So when we talk about heat loss and heat absorbing, if something is losing heat, there has to be something else gaining that exact same amount of heat. And that's where that whole surroundings and systems come from, that you looked at on the other set of notes from Tuesday. Um, so remember, system is what we're actually focused on. It's the actual process. The surroundings is basically kind of what's holding it. So if you had a reaction in an Erlenmeyer flask, the reaction going on inside the flask, that's the system. How the flask would fill, that's the surroundings. Okay. All right, so here we go. So example number 1. So a metal pan contains 2.00 times 10 to the 3 grams of water. If the pan is at room temperature, which is 25 degrees Celsius, how much energy must be applied to bring it to the boiling point at 100 degrees Celsius? Specific heat of water is 4.184 joules per gram degree Celsius. Unless we are asking you to calculate specific heat, which is C, unless we're asking you to calculate C, we will always give it to you. So you always read your problem. It is definitely beneficial for you to make a list of your variables. Okay. So anyway, so we're going to go through. So the first number I see the mass of my water. So I'm going to put that there because it says grams. Next thing I see is that it's at room temperature, and it wants to know how much energy to bring it to boiling point. So we're starting at room temperature. So that's my initial. My final is going to be 100. And then it tells me my specific heat of water is 4.184. And it asked how much energy. So energy is Q. Now notice I don't have a value for delta T. You don't have to have a value for delta T. Okay, if you have a value for delta T, you don't have to have a TF or a TI. Okay, so delta T, like that's just in case it only gives you one temperature. Like if it says, and it changed by 30 degrees, that would be a delta T. But this one is not saying how much it already changed. It's telling you where it started and where it's going. All right, so since we want to find Q, we cover up Q over here. And notice all of our letters are side by side. So our equation becomes Q equals M times C times delta T. Remember that delta T just means change in, so it's final minus initial. So all I did was substitute TF minus TI instead of the delta T. Yes, you can calculate delta T and then put it in there. That's perfectly fine. I didn't want to do that because that's just extra. So mass times the specific heat times the delta T, and our final was larger than our initial. And you put it in the calculator, and this would be the acceptable answer. I just put this extra answer there because you've been used to seeing kilojoules. But this is what you're looking for, 627,600 joules. Example number 2. How much energy must be absorbed by a 45-gram copper cube to increase its temperature from 40.5 degrees Celsius to 230 degrees Celsius if the specific heat of copper is 0.386? So notice how it's saying it's absorbed, so we should be looking for a positive number in the end. So that's what we're looking for. Once again, we're going to do the same thing. 45 grams, that's our copper. It's changing temperature from 40.5 to 230. So initial is 40.5, final is 230. Tells me my specific heat is 0.386, and it also asks how much energy. So I'm looking for Q. So once again, I cover up Q because that's what I need. Q is equal to M times C times delta T. I plug in my numbers. Actually, I changed that again. Remember, so I don't use delta T. Like I said, you can go ahead and calculate delta T and then substitute that in there. But I mean, if you're going to calculate it anyways, you might as well just put it in the equation. So that's what I choose to do. All right, so then I end up with 3,291.62 joules. Notice how it is positive. That's good because it says energy was absorbed. Just like our last problem, which I forgot to ask, our last problem also wanted to know how much energy must be applied. So if you are applying energy, that means you are giving in energy. So like, like you have to apply it. So it has to be applied to that thing. So that thing, whatever it is, that pan of water, in order to get it to go to 100 degrees Celsius, you're applying heat or energy to it. So it's taking in energy. So that's also really positive. Okay, so that was example number 2. All right, so example number 3. A 15.75 gram piece of iron absorbs 1086.75 joules of heat energy, and its temperature changes from 25 degrees Celsius to 175 degrees Celsius. Calculate specific heat capacity of iron. So this one's a little bit different. Still do the same steps. Pick out what you're given, what you're asked for. So I have my mass. It tells me that I'm going from 25 degrees Celsius to 175 degrees Celsius. So 25 degrees Celsius, my initial temperature. 175 degrees Celsius is where I'm stopping or where I'm going to end. And this time it gives me how much energy I absorb. So therefore that's a positive number because we're absorbing it. And it's asking me to calculate C. So that's the only difference. All right, so now I want to calculate C. So I'm going to cover this one up. Notice how it's top and bottom. So Q is on top of M and Q is on top of delta T. I mean, it's just plain division. So to get C, it's Q divide by M divide by delta T. That's all you're doing because Q is on top, M and delta T are on bottom. So you're going to divide by both of those numbers. And that's all we're doing there. So Q divide by M divide by final minus initial. Plug in your numbers. Get your answer of 0.46 joules per gram degree Celsius. This specific heat is specific to every substance. Every substance has a specific heat. 0.46 is irons. Okay, that's what we're going to be doing on Monday. Your first part of it is going to be identifying an unknown metal based on its specific heat. So this is what you're doing then. All right, so example number 4. How many joules of heat are needed to raise a temperature of 10 grams of aluminum from 22 degrees Celsius to 55 degrees Celsius if the specific heat of aluminum is 0.9 joules per gram degree Celsius? Same process. Pick out your numbers. There's my mass, my initial temperature, final temperature, and it gives me specific heat this time because it's asking me how many joules of heat. If you're asked for joules, you're asked for heat. That's your Q. So I cover up Q. They're all side by side. So Q equals M times C times delta T. Q equals M times C times final minus initial because that's what delta T is. Once again, yes, you can calculate delta T and then just substitute it. Plug in your numbers, put it in your calculator, boom, 297 joules. All right, this next section is specifically to help you with your lab next Monday. So please make sure you get this down in your notes because this will be something you probably want to refer to. So your lab on Monday, you're doing specific heat of a metal and then also calculating how many calories are given off by a single cheese puff. And to do that, we can't measure that directly. Like we can't measure the metal directly. We can't measure the Cheeto directly. We have to do through changes of temperature in water. So this is what that's going to, okay? So a 55 gram mass of a metal was heated to 100 degrees Celsius. Then it was plunged into 100 grams of water at 24 degrees Celsius. The temperature of the resulting mixture became 28 degrees Celsius. Specific heat of water is 4.18 joules per gram degree Celsius. So let's talk about what's happening. So I have I have metal, I've heated it to 100 degrees Celsius. I have a cup of water, it's at 24 degrees Celsius, and there happens to be 100 grams of it, so there's 100 milliliters of it. I then stick the metal into the water, and once I do that and I let it sit, for a while, both become 28 degrees Celsius because because the metal and the water are together, so they're going to end up at the same temperature. Okay. This one is specifically asking about how many joules of water, and it's important to pay attention because you're given 2 masses up there. You're given a total of 3 different temperatures. So you got to figure out which one you're supposed to use. So our first thing is the mass we use. We're asked about joules of water, so we need the mass of water. Second thing, we need, since we're asked about water, we need the initial temperature of the water. So initial temperature of the water was 24. They both become 28 degrees. Okay, that's the final temperature of both of them. Our specific heat of water is 4.18 because we're asked how many joules. So we are looking for Q. All right. So Q is equal to M times C times delta T. M times C times final minus initial. We get 100 times 4.18 times 4, and that comes out to 1,672 joules. So that's just a regular old calorimetry problem, but you got to make sure you pick out the correct numbers. Make sure you pick out the ones that are for the water. Pre-lab 1B. So what it wants to know now is how many joules did the metal lose? So think about it. If the water is absorbing the energy, where does that energy come from? So remember what I was explaining earlier, that if something is losing energy, something else has to be gaining it. Okay, it can't just be lost and then that's it. Something else has to gain it because we have to conserve energy. So what we have going on is we had a hot metal put into a cup of water that was relatively cold, and then the water heated up, but the metal cooled down. So where did the water get its heat from? Well, or its energy, because that's what we're measuring. Heat is energy. It came from the metal. So the metal lost its heat to the water. Well, if the water absorbed 1,672 joules, and we have to conserve energy, that means it has to be the same number, then that means that the metal lost 1,672 joules. Okay? So it's the same number but opposite sign because it lost. Now is where we're going to calculate specific heat so that you can actually go identify the metal. We're not identifying the metal in the example, but you are going to calculate the heat. So once again, the reason why I'm including the stuff from before is because with this, what you're being asked is now you're asked to calculate specific heat of the metal, but you still need the information from before, okay? Because we need to know what the mass of the metal was. We need to know what the initial temperature of the metal was. We need to know what the final temperature of the metal was. And all of that came from previous information, along with how much heat was lost, which came from B. Okay, so 55 grams, because now we want the metal. The metal was finally, like its final temperature, remember both of them was 28 degrees Celsius. However, its initial temperature was 100. So it was heated to 100 and then dropped into colder water, which made its temperature decrease, but the water's increase. We also know, like, we're not using this specific heat because it says specific heat of water. We don't want that because we're looking for specific heat. We also know that since the water absorbed 1,672 joules, that means the metal lost that same amount. So we know how much heat it lost. Okay, and because it lost, that's a negative number. So we have our Q. We are being asked to find specific heat. So we're looking for C. So once again, we cover up C. Notice how it's top bottom, so it's Q divided by M divided by delta T. So we have C is equal to Q divided by M divided by delta T because you're taking the Q and dividing by both numbers, and that's just the easiest way to do it. Okay, that's what you're doing. So Q divided by M divided by final minus initial. Our Q this time is negative. Our delta T, our change in temperature, is also negative because you can't have a negative specific heat. So you gotta have, like, if we didn't have a negative delta T, we would end up with a negative specific heat, and that doesn't work. Okay, it is a negative delta T because remember the initial temperature of the metal started off really hot. Then it went into cold water. So when it went to cold water, it starts to cool down as the water heated up. So the metal cooled down to 28 degrees Celsius. So that's why it's a negative delta T. And this came out to 0.42 joules per gram degree Celsius. And that is how you're going to end up doing one part of your lab on Monday. It's the same thing for the actual Cheeto, but it's just, there's not like something being added to water. You're really only calculating one thing and then assuming that the other one lost the same amount is really all you're doing. You're only doing like part of this thing for the Cheeto Lab. Anyways, you have a practice called calorimetry practice 428. Please make sure that you complete that. If you need scratch paper, I have scratch paper, or you do your own scratch paper, whatever you want. An expo marker you can draw on the desk, that'll work too. All right.